Alright, so section 4.4, concavity and curve sketching. So we're going to use all that we learned in 4.1 and 4.3, and we're going to add one more concept, and then we're going to be able to graph these curves with a high degree of accuracy. So let's introduce concavity. So let's consider f of x, which is equal to x cubed. Now, if you look at this, the graph of this function, what we have is positive side looks like this, and the negative side looks like this. Now, I chose this curve because it changes concavity at x equals 0. This piece right here is considered concave up. So this part right here would be concave up, and over here this one would be concave down. So concave down. So concave up looks like a U, looks like this. Concave down would be like this, okay? So that's kind of the idea, is that there's your concavity down, this is your concavity up, so like a U up or a U down. So concave up has something that looks like this, that's concave up, and concave down looks like this. So something like that would be concave down. Alright, definition. So we got a hard definition for this. Hard, I mean a clear definition is kind of what I mean by that. So concave up and concave down. The graph of a differential function y equals f of x is, so A, we have concave down. Let's do concave up. Concave up first. So concave up on an open interval I if f prime of x is increasing on I. So it means the derivative is increasing. So let's kind of see what's going on here. So the derivative of this function is increasing, like say this piece right here, because right now the derivative would be negative, then the derivative would be 0, and the derivative would be positive, and more positive, and more positive. Can you tell the slope of this pen is increasing as I cruise through this curve? So all the way up here, the slope is really positive. So what it means is that the derivative is actually changing, that the slope of the tangent line is increasing as you move through this curve from left to right. And then very similarly, concave down on an open interval if f prime of x is decreasing on I. So what we have is we have a test to be able to do this, and this is called the second derivative test. So let f of x be twice differentiable. Means it has a second derivative on an interval I. So 1, if f double prime of x is greater than 0 on I, then the graph of f over I is concave up. And then the second one, or B, if f double prime of x is less than 0 on I, then the graph of f over the interval I is concave. So what we're testing is we're testing to determine if the derivative is actually increasing. So the way that you test the derivative is increasing is you take that thing's derivative. So that's why we're taking the second derivative here. So remember that it says it's concave up if the derivative is increasing. So how do you determine if this thing is increasing? Well, you take this thing's rate of change and see if it's positive. If this thing's rate of change is positive, then you know it's concave up. If this thing's rate of change is negative, then you know it's concave down. So its rate of change would be the second derivative in both cases. So the second derivative is positive, concave up. The second derivative is negative, concave down. So apply. Let's do a quick example of determining concavity. So apply. So we already know x cubed, and I've already shown you what part of this thing is concave up or concave down. So what we're going to do is we're going to take this thing's first derivative and its second derivative and determine when the second derivative is positive and the second derivative is negative. So the second derivative test means I have to take its second derivative. So we know that so the solution here. Determine concavity. This is what we're doing. We're determining concavity. So f prime of x is equal to 3x squared, and f double prime of x is equal to 6x. So this is its derivative. So what we're going to do is I'm going to basically cut the entire x-axis where this thing is equal to 0, and then I'm going to do essentially test points for the interval. So if you look at the entire x-axis, where is this thing equal to 0? Well, if I look at 6x equal to 0, this is when x is equal to 0. So we have a cutoff right here. So I know that this thing is equal to 0 here, so it's the only spot where it's going to change signs. It's either going to be positive over here or negative over here. And the second derivative is either going to be positive over here or negative over here. So what we're going to do is we're just going to do a test point like we did before. So I'm going to pick an x, let's say -1, and then also +1, and I'm going to go f double prime of those x values. So 6 at -1 is equal to -6, and 6 at +1 is equal to +6. So what I can tell is that the second derivative, f double prime of -6, is less than, that's rough, is less than 0, and then f double prime of +6 is greater than 0. So what that means is we have this right here. F double prime of this entire interval is going to be positive, and f double prime of this entire interval is going to be negative. So remember, again, 0 is the only spot where this thing changes sign. So I only have to test one point in here. I don't have to test any more points. And same with this interval. I'm going to have to test one point in this interval because the only spot it can change signs is right there. So that means we are concave up on this entire interval. So this is going to be -infinity. It's going to be concave up from this interval over here, so -infinity to 0, and it's going to be, I apologize, it's not concave up, it's negative, it's concave down. And this is going to be concave up on this interval, so from 0 to infinity. It's rough not having you guys here to fix my mistakes. Keep me honest, but I'll try to keep them at a minimum. So there we have it. So that kind of verifies our graph right here. We knew that it was concave down over here from -infinity to 0, and it's going to be concave up from 0 to infinity. So it shows that that's the case. All right. B. I'm doing simple ones. We'll get to more complicated graphs in a second here. F of x is equal to x squared. So in order to take its, to do the second derivative test, what I have to do is I have to find its second derivative. So f prime of x is equal to 2x, and f double prime of x is equal to 2. So again, what we do is we look at, we're going to look at the entire interval from minus infinity to infinity, and I'm going to figure out where this is equal to 0. And then I'm going to test points wherever, on either sides of all these, of all the zeros. So if I set f double prime of x equal to 0, so 2 equal to 0, what we notice is that this has no solution. 2 is not 0, so this has no solution. Therefore, f double prime of x is never equal to 0. So that means this entire interval, it's going to be either concave up or concave down. So I'm just going to pick a point. I'm going to pick a point in this interval. I know it's a little ridiculous, but I'm going to pick a point in this interval. Let's just say 0, and I'm going to plug this thing into this function. I'm picking 0 because it's the easiest number to usually work with, but to be honest, you can't plug anything in this function. It's got no variable. So when I test this entire interval, if I test x and say it's going to be 0, and I'm going to go f double prime of that 0, so f double prime of 0 is equal to 2, because everything is equal to 2. So what I notice is that f double prime of x it's always positive. It's always positive. So that means this entire function is concave up for all of it. And now if we go back to the graph to kind of verify this, I want to verify that since this entire thing is always concave up. Now remember, we could have picked 0 or we could have picked 1, right? It doesn't really matter. Any number will make this happen. It doesn't matter what's in this interval. What number in this interval, I mean. So if I want to verify, if you look at x squared, what you can see is x squared looks like this. And we can see that x squared is the perfect candidate for an entire graph that's concave up. It's all concave up. All right, inflection points. So a point where the graph of a function has a I just want to make sure that my definition makes sense. Point of the graph has a tangent. Okay, so it says has a tangent line. I got this from the book, but so a point on the graph where it has a tangent line and where the concavity changes. I see why they did this. Is an inflection point. Never judged it before, but now I kind of understand. So they don't say that it just has to be differential. They just said it has a particular tangent line. So what we know is there's a graph out there that looks like this, right? And I know that it's not differentiable at this point. But this thing, even though it's got a vertical tangent line here, it still actually is a spot where this thing changes concavity. So when you look at this graph, I'll do this and I'll come back to this in a second. So graphically, like an easy one would be something like this. We can see this graph does this and then this. So the inflection point of this particular graph is where this thing changes concavity. And we can see that it changes concavity right there. Because to the left of this, all this is, concave up, right? Oh, it's messy. Concave up. And over here, this is concave down. This piece right here, and this is called our inflection point. Now, I know we usually read left to right, but there's a kind of a funny little joke here that math teachers usually say. So when you're in if you're, let's go back to this. You can see that this piece right here, it's got an inflection point right there, right? So when you're on a roller coaster, you know when you hit the inflection point because it's the spot to where your butt finally hits the seat again. So you're coming over this crest, and you kind of come out of your seat, and as soon as your butt actually hits the chair again, that's the spot where the inflection point is. So that's what mathematicians do. You know, we leave our arms up. I wish you could see me. I got my arms up. So you leave your arms up, and then as soon as my butt hits the seat, we all say inflection point. But we don't because we're not total nerds. But maybe we are. All right. So this is also the inflection point because you can see over here this part is concave down and this part is concave up. So this particular definition allows for this particular function. It just doesn't say it has to be differentiable. It just says a tangent line must exist. So even with x cubed, if you look at another graph like x cubed is like this. Should be more flat, but oh well. So that right there is x cubed, and you can tell that this is that this point right here is our inflection point again. So this is also an inflection point. Concave down, concave up. All right, so what we need is we need a theorem to be able to find those inflection points. It's funny as we've actually already found them, and just haven't defined them yet. So here's a roller coaster. I'm going to move this. It's too busy. So theorem 5. Points of inflection. I don't usually label the theorems, so they're in the book, and I'm not even sure. I'm just going to say theorem. The book might not even name it 5. So theorem, or, ooh, this is not even a theorem. This is a definition. Oh, I got to start over. Definition. Points of inflection. So a point where the graph of a function has a tangent line and geez, Pete. It must be early. I already wrote this. Well, it gives you time to breathe. So, there we go. This is theorem 5. I was actually on a theorem. Theorem, second derivative test. It's a good thing I'm recording this. 4. So in many cases, we were able to figure out local extrema before because we cut our interval at a particular piece. And actually, I can use some messiness here. So what we used to do before in the previous section is we'd cut the interval over here at like some particular c value. And then what I'd do is I would pick an x value in here, and then I'd pick an x value in here, and then I would test this using f prime. Now if f prime of x1 was positive, I know that this thing would be increasing. And over here, if f prime of x2 was negative, I know that this would be decreasing. So if it's increasing here and then decreasing here, what I know is that's going to be a local maximum. But we have a new thing that we've actually learned is notice that this graph is concave down, right? So this test still works and it's useful because sometimes we have funny graphs to where you have to go back to this. But many graphs you can actually just say, hey, look, f double prime of c would be negative because this is concave down. So if you know the first derivative is equal to 0 and the second derivative is negative, then you know the first derivative being equal to 0 would give us a horizontal tangent line, so it's a candidate for a max or a min. And if the second derivative is negative, it's concave down. Therefore, this thing has to be a maximum. So that's what I'm going through right now. So suppose f double prime is continuous. on an open interval that contains C. X equals C. Let's say X equals C. 1. If f prime of C is equal to 0 and f double prime of C is less than 0, then f has a local maximum, just like the picture I showed. At x equals C. 2, if f prime of C is equal to 0 and f double prime of C is greater than 0, then f has a local minimum, because this means horizontal tangent line, this means concave up, so that means I have to have a local minimum right here. Now, the second derivative test is not always valid. There are times when the first derivative is 0 and the second derivative is also 0, and that actually means the test is inconclusive. So what you'd have to do is you'd have to go back to the first derivative test and figure out if this is increasing and this is decreasing, then it's got to be a maximum, or reversed, it would have to be a min. So we always have the first derivative test if the test fails. So if f prime of C is equal to 0 and f double prime of C is also equal to 0, then our test fails. Means it's inconclusive. So what that means is C might be a maximum, C might be a minimum, C might be a saddle point. We don't really know. All right. We're going to start graphing some curves, but our strategy is extensive. So this is the problems in this section are a little lengthy. But useful. So strategy for graphing f of x. So what we're going to do is, one, we're going to identify the domain. Of f of x. 2, we're going to find the derivatives. We're going to find f prime and f double prime. 3, we're going to find the critical points of f and determine the behavior at each. What they mean by this is when you find the critical points, it's where the first derivative is equal to 0 or undefined. And when they mean by behaviors, they want to know, is this a local max, is this a local min, is it a saddle point? So we're going to look at their behavior. And we're going to use the second derivative to do that most of the time. If not, we're going to use the first derivative test to see if one side's increasing, the other side's decreasing, then we know it's a max. Okay, so number 4. We're going to find where the curve is increasing, because sometimes the second derivative doesn't work. So we're still going to find where the curve is going to be where the curve is increasing and decreasing, and that's just using the first derivative test. We're going to figure out when this is positive and this is negative. Okay. 5, so we're going to cut our intervals just like we did in the third section. We're going to find the points of inflection. So this is where the f double prime is equal to 0. If any. Ooh. If any. And determine concavity. So the second derivative test mirrors the first derivative test. We find where the first derivative is equal to 0. We cut those intervals, and then we test points in those intervals to see if it's increasing or decreasing. F prime is positive or negative. And then we also want to find the inflection point. So we set the second derivative equal to 0, cut our interval, and then we do test points in the interval to figure out if the second derivative is positive, the second derivative is negative, the second derivative is positive, it's concave up, second derivative is negative, concave down. So this is very similar to the first derivative test in practice. Its results mean different things. The results of the first derivative test shows increasing and decreasing. The results of the second derivative test shows concavity. Identify any asymptotes. And then finally, we're going to plot every one of these. So we're going to plot key points. Now, what we mean by key points is, I'll give you the candidates of x and y-intercepts. So this is when the original function is equal to 0 for this, and when the output is equal to 0. We're also going to find the extrema, so your local maxes and your local mins, and inflection points. What's kind of neat is we're basically finding the zeros of everything. So the x-intercepts are the zeros of the function. The extrema are the zeros of the first derivative. And the inflection points are the zeros of the second derivative. So we've been finding zeros for, our entire life. So we already know how to do these things. Now we know how to do derivatives, so we can find those. All right, so start out with polynomial first, because polynomials are the easiest to work with. So what I want to do is I want to graph the function completely. So f of x is equal to x cubed minus 3x plus 3. All right, so number one, we have to find the domain. So the domain of f, well, this is a polynomial, so the domain of f is minus infinity to infinity. There's no division, so there's no divide by 0 error. There's no even roots, so there's no square root of a negative number error. There's no logarithms in here as well, so that's why the domain is minus infinity to infinity. 2, it asks us to find the first and second derivative. So f prime of x is equal to 3x squared minus 3, and then f double prime of x is equal to 6x. I know it says to determine the behavior of these things. I guess we can still do this. We'll talk about the behavior, but sometimes it's just useful to do the first derivative test. So 3. What it wants us to do now is we want to find the critical points. So our critical points are when the first derivative is equal to 0. So this is when 3x minus, so I'm going to label this as critical points. So this is when f prime of x is equal to 0. So this is when 3x squared minus 3 is equal to 0. So that means 3x squared is equal to 3, so x squared is equal to 1. So x is going to be equal to negative 1 and positive 1. Also, it wants us to find the second derivative equal to 0. So this is, well, it wants us to determine the behavior at these critical points, so the behavior. So I can actually determine if these are max and mins. A lot of times you could determine if these things are max or mins very quickly. You can just plug them into the second derivative. Remember, if the second derivative is positive, it's concave up. So that means that thing has to be a minimum here. If the second derivative is negative, it's concave down. So that means that point has to be a maximum. So what is f double prime of negative 1? What is f double prime of positive 1? Well, f double prime of negative 1 is going to be 6 times negative 1, so this is negative 6. And f double prime of positive 1 is 6 times 1, so this is equal to positive 6. So that means this is concave down. And the first derivative is equal to 0. So this is a concave down means this. So this is a local. So x equals negative 1 is a so messy, is a local maximum. And for this one, it says x equals positive 1 is a local minimum. Because remember that this is positive when it's concave up, so it means it's a local minimum. All right, 4. We're gonna actually determine these using the first derivative test as well. So 4 says we're going to use our first derivative test, and we're going to figure out where the function's increasing or decreasing. So using the first derivative test, we know that if we look at our interval, so this is our x-axis, we know that it's cut at -1 and +1. So our intervals are -∞ to -1. It's going to be -1 to 1, and then it's going to be 1 to infinity. Now we're going to pick an x value, and we're going to determine if it's increasing here, decreasing here, and so on for this and this interval as well. So I'm going to pick a number that's one integer below it. So -2. I'm going to pick 0 because it lives in that one, and then I'm going to pick one integer above, so 2. So the next integer. All right, so I'm going to plug these. Remember, if I want to determine increasing or decreasing, right? I want to determine increasing or decreasing of the original function. I have to plug these into the first derivative. So what is f prime of x? So f prime of -2 is equal to, well, plugging it back into here, this is going to be equal to 3 times -2 squared minus 3. 3 times 4 is 12, minus 3 is 9. So this is equal to 9, which is positive. Since it's positive, that means we are increasing. First derivative is positive. F prime of 0 is equal to 3 times 0 squared minus 3. So this is equal to -3. So this is negative. That means the first derivative is negative, so we are decreasing. And then here, f prime of 2 means 3 times 2 squared minus 3. So even function, let's give it this 12. So this is going to be 12, nope, not 12. 12 minus 3. This is 9. So this is also positive. So this is going to be increasing. So interval increasing, decreasing, increasing. Number 5. We want to test, we want to find the inflection point and also test concavity. So, inflection point. The inflection point is when f double prime of x is equal to 0. So that is when 6x is equal to 0. So divide both sides by that, you get x is equal to 0. So what that means is we're gonna pop this into an interval again, and we're gonna cut it at 0. And we're going to do the exact same thing that we did for our first derivative test, but this is going to be our second derivative test. So that means I'm going to pick an x value, and then I'm going to do an f double prime of x. So an x value in here, I'd say maybe -1, x value here, +1. And what's nice is we've actually already found those values, so I know that f double prime of -1 is equal to -6, and f double prime of +1 is equal to +6. So that means this interval, I didn't label it, I should have labeled the interval. The interval from -infinity to 0 is concave down. And the interval that goes from 0 to infinity is, since the second derivative is positive, is concave up. What's nice is we have a lot of information about the graph. I know when it's increasing, I know it's decreasing, I know it's increasing. So I also know where it's concave up and concave down. So a lot of information. So number 6. Does this thing have any asymptotes? No, unbelievable. far as asymptotes, remember asymptotes happen, vertical asymptotes happen with your ratio functions. So since the denominators, since it has no denominator other than basically 1, there are no asymptotes here. So you'll see these, because I'll have you graph a rational, or at least something that's a ratio of 2 functions. And then you'll see some asymptotes. All right, 7. We're going to do some extrema. Well, let's find all the things that it asks us for. So, x-intercept. Well, the original function was x cubed minus 3x. So this is when y is equal to 0. So 0 is going to be equal to x cubed minus 3x minus 3. Ooh, let's see. I don't know if I'm going to find any. I don't have a strategy for that one. There's a cubic equation. Like there's a quadratic equation, there's a cubic equation. Did I ever find one? Let me see if that would work. No, I skipped them because it's messy. Alright, tell you what, let's just look at the extrema values. Here, let me show you this equation. I guess we're at it. Oops, how we got it. Okay, Google. Cubic equation.
According to Wikipedia, in mathematics, a cubic function is a function of the form where the coefficient...
Let me know. You know, I'm not going to waste your time. I wouldn't make you guys solve a cubic unless it was easily solvable. So I'm just gonna. What we're gonna do is we'll just go to our extrema. If it's quadratic, you should be able to find the intercepts. So we know there the local extrema was x equals -1, and we know that this thing was a maximum. I think we labeled it. Let's make sure we have this here. We know that x equals -1 was a maximum. X equals +1 was a local minimum. So this was a maximum, local max, and x equals +1 is a local min. So what would be nice is if I could figure out the y values of these things, because I want to plot these particular points. So what I'm going to do is I'm going to plug them back into this original function. So remember, f of x is equal to x cubed minus 3x minus 3. So f of -1, so I want to know the y value of this thing, is going to be equal to, plugging this in, -1 cubed minus 3 times -1 minus 3 gives me 5. And f of +1 is going to be equal to +1 cubed minus 3 times +1 minus 3. And this is going to give us 1. Inflection points. The inflection point that we found was x equals 0. So again, it would be nice to know the y value of this inflection point. So I'm going to plug it back into the original function. F of 0 is going to be equal to 0 cubed minus 3 times 0 minus 3, which is equal to -3. Which actually happens to be the y-intercept of this function, so I guess I don't even have to find that. So now I have some points here. This is the point -1, 5. This is the point 1, 1. And this is going to be the point 0, -3. So what we're going to do is we're going to graph this function. I'm going to plug those points in right now, so I know I have -1, +5, 1, 2, 3, 4, 5. And then I also have +1, 1 there. And then 0, -0, -3. Let me make sure. No, this is a +3. It's beautiful. My points are not wrong though. This is a +3. Those are actually correct from my notes. Okay, so graphing this, we're going to have negative 1, 5, which is going to be right here. You're going to have 0, comma 3, which is right here. And then you're going to have 1, comma 1, which is right here. Now what's nice is I know that this thing is a local maximum, so I also know that it was concave down, so it's going to have like this little arch that looks like this. And I know this one was a local minimum, so it's going to have, another local arch right here. Now remember, this is a point of inflection. So I think you could probably see how this is going to work. But when we get to the more complicated functions, it would be nice to kind of make sure that we're doing everything we can. So when we go back to our function, I know that from 0 to negative 1, I know that this thing is increasing. So the function from 0 to negative 1 is going to be going uphill. Now there's a couple different ways that you can go uphill. There's a couple different ways you can go uphill. You can go uphill this way, or you can do it this way. So this one being concave up, this one being concave down. So we have to pay attention to concavity as well. So when I graph this function, I know from 0 to negative 1 it's increasing, but also from negative infinity to 0, from negative infinity to negative 1, from negative infinity to 0, this thing is concave down. So on this interval from 0 to negative 1, it is both increasing and concave down. So it's going to be increasing and concave down. So the only way to do that is it's got to be increasing concave down. It's got to look like that. So what I know is it's got to be something like this. It's got to be increasing and concave down. Now I'm going to look at this little piece here. So I know from negative 1 to 1, so from negative 1 to 0 is all I'm looking at right now, but from negative 1 in this area, I know that this thing is decreasing, and I also know that it's concave down as well. So this has to be right here decreasing concave down, so it's going to look like this. So I know that it was concave down through this entire interval from 0 to negative 1, but from negative infinity to 0, but from negative infinity to negative 1, increasing, decreasing. Now, back to this, we know that it is still decreasing until I get to 1, so it's going to be decreasing, but it's also going to be concave up. So it's decreasing concave up, and then over here it's going to be increasing concave up, so increasing concave up, it's going to be like this. Now, I'm telling you we can find this x-intercept if we really dug, but I'm not going to force you to find the x-intercept of a cubic. There's a quadratic edge here. All right, pretty graph, huh? All right, next. Let's do another polynomial. Sketch. So when I ask you to sketch, I'm not going to go through all the numbers again. What I mean is you have to do steps 1 through 8. So f of x is equal to x to the 4th minus 4x cubed plus 10. So 1, domain of f, minus infinity to infinity. 2, we're going to go a little quicker. F prime of x is equal to 4x cubed minus 12x squared. F double prime of x is going to be equal to, so the derivative of this is 12x squared minus 24x. 3 critical points. F prime of x is equal to 0, so when 4x cubed minus 12x squared is equal to 0, pulling out a 4x squared, I'm going to get x minus 3. So 4x squared equals 0. And x minus 3 equals 0, so I get x is equal to 0 here, I get x is equal to 3 here. Now it also says to determine if they're max or min, so it says determine their behavior. So I'm going to plug these into the second derivative. So these are our critical values that are going to go into here. So f double prime of 0 is going to be equal to 12 times 0 squared minus 24 times 0 is equal to 0, which means the second derivative test fails. Here, it's inconclusive. Now, if f double prime of 3 is going to be equal to 12 times 3 squared minus 24 times 3, and this one gives me 36. So this is positive, so that means we are concave up. So this is 0 and concave up, so that means that we are local minimum. So x equals 3 is a local min. I don't know about 0. I bet you it's in the function. We'll know in a minute. 4. What we're going to do now is we're going to first derivative test. So I know the first derivative is equal to 0 at 0 and also at 3. So our intervals are going to be minus infinity to 0, 0 to 3, 3 to infinity. Picking an x value, I'm going to pick -1, I'm going to pick a +1, and then I'm going to pick 4. So plugging this into the derivative, f prime of -1. So f prime of -1 is equal to, when I plug it into this function, just take my word for it, it's going to give you -16. Remember, you can use your calculator if you want to find these values. F prime of 1 is equal to -8, and f prime of 4 is equal to 64. So since this is negative, and this is positive, that actually kind of verifies this this local min at 3, right? It's going downhill here and uphill here, therefore it's got to be a local min at 3. Do you see why the test was inconclusive here? The increasing or decreasing, it just decreases, then it continues to decrease, so it's probably a saddle point there. So that's why this came out inconclusive. So that means decreasing, decreasing, increasing. Number 5, inflection points. So f double prime of x is equal to 0. So if I do 12x squared minus 24x is equal to 0, I can pull out a 12x, and I'm left with x minus 2 is equal to 0. So for this one, you get x equals 0. For this one, you get x equals 2. So now I have to test the concavity at each one of these as well. So what I'm going to do is I'm going to, so this is going to be a second derivative test. So cutting our intervals, I'm going to go at 0, and then I'm also going to go at 2. So our interval is going to be minus infinity to 0, 0 to 2, 2 to infinity. So I'm going to pick an x value, and since I'm doing the second derivative test, this is going to be f double prime of x. So it's -1 here, let's do 1 here, let's do 3 here. So I know f double prime of -1 is going to be equal to 36. I plugged these in my calculator beforehand. So f double prime of +1 is equal to -12. Why am I getting more? Oh, I'm not doing it. F double prime of prime of 3 is equal to, I know what it is. Picked a different number. Like a dummy. Alright, let's see. I bet I can plug it in there. F double prime of this. Let me plug this in. Yeah. So I have 12 times 3 squared minus 24 times 3 gives me 36. Oh, I already plugged it in. Dang it, it's right there. 36. Okay. So what I know is that this is positive, this is negative, and this is positive. So I know that this is concave up, this is concave down, and this is concave up. Alright, so Number 6. There's no asymptotes. It's a polynomial again. Number 7. It's a 4th degree polynomial. Again, I'm not going to make you guys solve for x-intercepts of these, because they're really complicated. So what I'm mostly looking for is extrema and inflection points. So extrema. So what we know is that I have a local min at x equals just 3. So plugging this back into our function, remember f of x is equal to x to the 4th minus 4x cubed minus 10. So f of 3 is going to be equal to 3 to the 4th minus 4 times 3 cubed minus 10. So f of 3 is equal to negative 17. So this gives us point 3, negative 17. I don't have inflection points. I actually have 2 of them. I had, back to the inflection point, we had one at 0 and also one at 2. So x equals 0 and also x equals 2. So f of 0 is going to be equal to negative 10. That was a quickie. And then f of 2 is equal to 2 to the 4th minus 4 times 2 cubed minus 10. So this gives us negative 6. So I have the point 0, comma, negative 10. I also have the point 2, comma, negative 6. So let's plot this to the best of our ability. So alright, so I know that I have to do 0, negative 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I also have 3, negative 17. So 10, 11, 12, 13, 14, 15, 16, 17. Okay. I also have to go, trying to screw anything up. Oh, this is positive 10. Why, did I do that again? I sure did, man. Stinker. Okay, this is positive 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so negative 17, this is positive 10. All right. There we go. So first I'm going to graph 3, negative 17. So 1, 2, 3, negative 17 is right here. 0, comma 10 is right here. 2, comma negative 6. 1, 2, 3, 4, 5, 6 is right here. All right. Now, remember that we have to assess all the increasing, decreasing, and concavity, okay? So, going back to this, what I know is from minus infinity to 0, so right here, I know that it is decreasing. I know it's decreasing here. And also, it is concave up. So, decreasing concave up would mean it'd have to look like this. It's got to decrease. So, remember our concavity. Decreasing could look like this, or decreasing could look like this. This is the one that decreases concave up. This would be decreasing concave up. So decreasing concave up means it's got to look something like this. Now I also know from 0 to 3, so I'm going to go from 0 to 2 right now, but from 0 to 2 it is decreasing, and from 0 to 2 it is concave down. So this is going to decrease concave down, so it's got to look like this. Remember that this is an inflection point at 0, so it's going to be one of those vertical inflection points. I'll come down and hit this in a second. Messy, okay? And I know that it's going to be decreasing from 0 to 3, so it's still going to decrease to hit this. It's got to. And it's also going to be, well, once I'm beyond 2, it's going to be concave up. So it's going to be decreasing concave up, so it's going to look like this. I'm going to pull these points a little farther apart so you can see them. So, let's see. And then the next thing we have is from 3 to infinity, it's going to be increasing, and it's also going to be concave up, so it's going to look like this. So what I was trying to pull off, and here's a kind of a better shape of that, is it looks like this. It flattens out at that maximum. It goes concave down to a vertical, and then it increases up to this. So these being our 3 points, okay? Those being the 3 points. So it has that particular shape is what I'm trying to show you. So decreasing concave up, decreasing concave down, decreasing concave up, increasing concave up. What will probably help you, and I'll give you a strategy, is see how close my points are. Would have been a little bit nicer is if I did 1 here, 2 here, 3 here, and stretch this thing out a little bit, and then it would be easier to show its shape.